Love Track sponsored by Lockheed Martin. My name is Maria Rodriguez.
My name is Daniel Garcia.
My name is Gerardo Diallo.
My name is Lucas Matus.
So the main problem you're solving comes from Lockheed Martin Arnold facility. They basically ask us to improve the way they manage inventory. Although it's basically to design and build a weather station that makes the process faster and easier to manage.
So now, we proudly present to you the results of months of collaborative work and applied engineering. The final prototype of the Stocktrack Pro, an intelligent solution for mobile inventory management within industry environments. On the left picture, you could see the 3D CAD design we conceptualized last semester as a team, and on the right picture, and right there, the physical results.
Okay, so this is a quick overview of the main product requirements, including mechanical, electrical, and software. So for the mechanical side, the station should be mobile, adjustable in height, and it should be strong enough to support 100 pounds of equipment. For the electrical part we should include like a lock mechanism and a power bank. And for the software, a clear organizer database should be included, and also a notification system that alert the user when parts are running low.
Here's our work breakdown structure for this project. As for the spring semester, we purchased and manufactured our inventory control system. We mechanically, electrically, and software tested our system, and then we tested our whole system. And now we're finishing our spring deliverables. As reiterated, here's the schedule. We completed the purchasing and manufacturing from December to February, and then we just finished our system testing, and right where the blue ticker is the spring deliverables, so we're completing them as well. Here are constraints and standards. So to start with the constraints, we focused on the health and safety, sustainability, economic, and time constraints. As far as health and safety goes, we rounded the corners of our station to prevent injury from the system. We're going to make sure that we design for overload protection system. And then sustainability goes, it does not require licensed personnel to complete this assembly. We had a company budget of $10,000, and this had to be completed within 2 semesters. We had to abide to 2 ASME drawing standards. We were USB Type-C compliant, and we followed 2 NEC codes. Here's our ethics codes. To be brief, we followed Section 2.1, Section 3.1b, and Section 3.9b. The reason why we chose these ethics codes was because we had to make sure our work was safe. If we thought our idea was not suitable for the project, we had to contact Lockheed Martin to make the appropriate change. And then the documentation, designs, and engineering created for this project is not owned by us, but that of Lockheed Martin. Here's our budget for the project. As indicated by the top right, is a red box indicating what Lockheed Martin supplied for the project. And the bottom right shows the total for the project. And then the real-world budget considerations. So 4 engineers work for 2 semesters, which is around 30 weeks of work. It would cost about $48,000. The licensing will cost $67.50, along with the budget price and Lockheed Martin supply of just over $8,000. The real-world budget total will be just south of $60,000. However, this does not include override costs.
This mobile station has some main features, and those are a touchscreen, a monitor arm, a wireless barcode scanner, label printer, 2 drawers, one for the key and one for the computer, a control panel located on the back side of the mobile station, handles to easily move the mobile station, and it has an overall height of 5.5 feet. This slide illustrates the mechanical drawer system of the Stocktrack Pro. On the left side, the sounding view picture highlights the location of the solenoid and the latch mechanism. Those components are installed on the back panel of the control panel labeled ACP and on the back panel of each drawer. Additionally, we designed a free space of 1.5 feet between the control panel back control panel and the back panel of the drawer to avoid overheating of the solenoids and ensure safe operation. The right picture indicates the exact location of this mechanism within the full frame of the mobile station. Moving into the mechanical testing, the first video demonstrates the functionality of the monitor arm. It is height adjustable, allowing users of different status to comfortably interact with the touchscreen. This enhances ergonomic use and adaptability. In addition, this monitor arm provides 360 degrees, allowing users behind the mobile station to easily access the touchscreen and use the software without needing to reposition the unit. The second video shows the control panel door, which opens fully to 180 degrees. This wide opening allows that the doors does not interfere with engineers while they are working with internal components of the control panel. And on the last video, you could see the mobile station moving forward, backward, and performing a rotational movement in place. Additionally, when a stationary operation is required, the wheels can be locked both in position and direction to secure the station and ensure stability during use.
So here's our testing for our key drawer, laptop drawer, and mobile station. We created a table that demonstrates our parameters required for experimental testing. Required, our key and laptop drawer head was extend fully by 20 inches. The max load for the key drawer was 3 pounds. The max load for the laptop drawer was 4 pounds. And then the max load of the mobile station that we initially wanted was 100 pounds. Experimentally, we found that these were all successful. Both drawers extended 20 inches. The max load for the key drawer was 10 pounds, and the laptop drawer was 8 pounds. And then we tested the max load of the mobile station was 200 pounds.
All right, so now let's go with the electrical design. This is the overall system diagram, which is pretty similar to the one that was presented last semester, but we also include USB hubs in and out of USB ports. As you can see here, every component, including laptop, printer, touchscreen, they are all connected to the same power source. Now that I am talking about the power source, this is the one that we are using, which is the EcoFlow Delta 3. It comes with enough capacity to supply power to every component, and also with enough AC and DC ports. Moving to the lock mechanism, this is the final version of the design. After we tested all the components, we put it all together in a protocol. We have some updates. We include two current sensors to keep track of the power that is going to each solenoid. And we also include a buzzer to notify if something goes wrong. Okay, so what you can see here is the main screen from our LabVIEW interface. For sure, whenever we go into the details later, but for now, just let's focus on the electrical testing results. So basically, as soon as a user presses the button to open here the key drawer, the computer drawer, LabVIEW sends a signal to the ESP glue, which will then unlock the drawer. If the current that is flowing through our solenoid is within the normal range, which is 330 milliamps, feedback message is sent back to LabVIEW and is presented like in right here. For this image, we try to simulate a fault by just disconnecting the power source. And this is the failure message that you will see here. Okay, so now we go to the power bank
summarizes the user access level in our system. First, viewer, regular user, and administrator can view parts on Windows. The regular user and administrator can inventory and remove parts, open key drawer, and print the labels. And the administrator is the only one allowed to open the computer drawer, add, edit, and delete users, parts, testers, and programs.
So now I'm going to be logging in as an administrator. I'm scanning my ID, and then I'm going into the menu page. I'm going to open the key drawer, and then the computer drawer stays open for 5 seconds. And then you can see the message displayed there, the feedback message. Then after that, I'm going to be printing labels. I'm going to be printing a part label and then also a shelf label, which is the same name as the testers at Lockheed Martin. And this works by just sending a string to an Excel file that generates a barcode. And then right now I'm testing the failure cases when the battery is disconnected, and you can see how the buzzer goes off, and then there's a burn display there. Now I'm going to the menu page as an administrator. The administrator can add, edit, delete, and see the whole user information. Right now I'm adding a new user, Dan as a viewer. After that, you can see the new user appear in the database. Then I'm going to edit the user as from a viewer to a regular user, and then you can see it appear again in the database, and then I'm going to be deleting the user. This works the same way if the administrator wants to add a new part. This works the exact same way if you want to add, edit, or delete a part. Then moving into the testers page. Here everyone can access this page, and they can see all the testers available in the database and all the parts. And they can just scroll through it and see all the related information for those parts. And then they can also look by parts. And then if they're a regular user or an administrator, they're going to be able to see those 2 buttons to add or remove parts. Now moving into the main parts page, this is the business page. At first, there's going to be a tab that shows all the parts available in the database, all the information for it. And then you can search by either program name, you can also search by the tester / shelf name, and also by part number. And then if you're a regular user or administrator, you can add here too and remove parts. Then after that, you can see all the programs and testers available, just the names of them. And then the administrator can add, edit, delete parts, programs, and testers. I'm going to show an example of like deleting a wrong part. I added like a system that like asks the user to check if they want to proceed with deleting this part, since it's like an important part of the database. And then they can proceed with this action. And then also you can print labels here for the parts to put in the boxes, and also for the shelves in the cabinets. And then you can see all the parts that are low, and then there's also a CSV file that's generated so they can load the parts. And then in the inventory page, over here you can just return a part to the shelves, cabinets. At first I'm looking for a part just to check the quantity of them. We have 0. And then I'm going to be putting the part number, scan the shelf, and then click OK. And then I'm going to look for the part again, and you can see how it goes up by 1. And then it works the same way when you want to remove a part, you just go -1 in the remove part page.
Just to conclude, the final design, planning, and testing phases have all been completed. The design milestones for mechanical, electrical, and software were all satisfactory. In addition, individual and full system testing were all successful as well, and stock tech code will be delivered next week to Lockheed Martin.
So finally, we would like to give an special thank you to all the engineers at Lockheed Martin to help us follow the project, and also to our senior project advisor, Dr. Su, for his guidance and feedback. That's it. Thank you so much.
This part, I agree with you. Slides 20, how long does it take? Slides 20, how long does it take to recharge that system?
It should take like an hour to fully charge the battery. Like an hour to fully charge the battery.
Is that acceptable?
You see what?
Is the recharging time acceptable?
Yeah, basically it should be only recharged like at the very end of the day. but it should be keep working like on a single charge. The entire like workday.
Okay, thank you on that. Second question, regarding this application was done here at the university,
Yeah.
this application of the congratulations on that, that's really good. From the price point, what would it cost for Lockheed to have another one of those, or multiple one of those, like the one you did, outside of doing the zero cost?
So, because of the override costs, so it'd be anything other than labor and material, we're expecting to probably be anywhere from $100,000 to $500,000. So,
Mr. Rachel, is that right? Say-
$100,000 to like $500,000.
He's asking if he wants to build one or.
Oh, building.
It's just a budget, like 4,000 something.
Oh, the budget? Yeah, it was around 4,000.
Okay, thank you.
$4,000, sorry. I didn't hear what you were saying.
It looked like that cabinet had room for more drawers. Is your system extensible for a larger, keeping track of a larger inventory? More drawers?
So, do you mean to have extension for drawers, right? So,
For extra drawers?
for extra drawers, so this mobile station is just designed for computer drawer where they will put the main brain of the system. That is that right there, the right drawer from the side is electronic, and the next drawer is for the keys because they want to maintain a security of all the programs and testers they have in the laboratory. So for now, we're going to have we have just two drawers, but if Lockheed Martin wants an update to have another drawer, we could put some below those drawers or maybe extend the size of the mobile station.
So these are the current like cabinets they have, and then they have like keys for each of them, so the keys are gonna be up top in our drawer in the station. You wanna access the cabinets.
This is
For the
not for
parts.
physical storage. It's not for physical storage.
Okay.
The storage is somewhere else.
So you had a slide on backup power consumption, it was from 100% to 25% in 1 hour, and you had some data for this. How was your testing procedure? The data are very linearly spread.
So basically, the board one provides like information on the board consumption, battery status, and the remaining roadmap. So I like keep track of that reading like for 10 hours, and that's what I presented here.
So the system was like in idle situation, you were not specifically doing anything with that for continuously like 9-10 hours.
So I try to keep it like, I think the output power was usually like 80 watts for the entire time. I was considering like using the under heavy load because I connected the touchscreen, I was also using my laptop, I was like recharging my phone, and I never let any of the components go to any sleep mode. So that's like under the heavy load.
So that was my question. It was using drawing power, and the power was used for laptop, charging laptop, phones. What about the solenoids? Are they constantly activated or no?
No, they are only just activated for 5 seconds.
When they're opening, so they are pull solenoids, not push solenoids.
So there's almost no power consumption.
I want another question. So about the testing, the load testing, you said that the max load, I think, was 100 pounds on the testing, and you tested for 200 pounds. I assume it didn't fail, right?
No.
So how do you know it did not fail? Did you check the loads afterwards, the location of them? It just didn't break, right? 200 pounds.
Yeah, no. Yeah, we checked the interface to see that everything was tightly secured, and it was.
Yeah, additionally, we know that the grid can support 220 pounds each month. So the maximum load taking into account the weight of the mobile station would be around 500 pounds. Additionally, we know that making some analysis that this mobile station could support easily 200 pounds.
Did you utilize finite analysis? Check the structural points, finite analysis on that, or was it required?
We were able to, because of the amount of components that the assembly had, do the finite element analysis for the whole system, but we were able to simulate the load and do more.
Yes, go. So as Lucas said, the only one that we were able to test or simulate was the hydraulic because of the amount of components. The entire amount of components of the mobile station in SolidWorks was around 700 components, so that's too much. And to test the hydraulics, the laptop drivers, the computer needed extra of 10 gigabytes of RAM memory to make it possible to run this simulation. So we were not able to run the entire mobile station, but just for the key. Yeah.
You don't need to model the entire setup. You just need to model the maximum force or multiple forces.
Yeah, we also tried
We
that.
started trying that as well, and it still was too many components.
Yeah. Because just the bottom part of the mobile station, that is the weakest part, it has more than 100 components. So SolidWorks wasn't able to run the simulation.
So, Maria, how many hours overall is this estimation? How many total hours you put in the software development? I just want to get a sense of it. Like just roughly how many hours?
I'm gonna say 100. Like I was like working every day on it, like because
No,
it was learning.
Is it like a 100, a 500, or 1,000? Like how many hours?
I think
Roughly.
like 100 because I had to learn LabVIEW from scratch.
Okay, but it's about 100, not 500.
More than 100.
Okay. So 6 full months. The reason I'm asking this question is just like I'm very impressed the way the kind of the software, always devils are in the details. And people, many of us wouldn't be able to understand. That's why I want to kind of just because that's the true hard work of engineering, which is the attention to details. Because people cannot spec those things for you. You have to. That's why you have to hold yourself to the highest standards as an engineer, because only you know this better than anyone. You know how to design a system to the best, highest quality, and for that, I really want to compliment you guys for that. Great piece of work, really very thorough, like a very like a vigorous, very rigorous testing, and lots of them trying to get rid of all the bugs as many as possible. I do have one question for Danny, which is like when the system is idle, you operate for like 10 hours, right, continuously, right, and didn't fail, and then there's no overheating any part of the system. Okay, so like you said, it's about 80 watts when it's idling, right? So what's the current? What you have a current sensor? What's the most of that? What's the current to draw?
Like you are looking like about the SolidWorks?
No, overall system. You have what's showing there? Is that the overall system or just the solenoid?
That's the overall system.
Okay. What was most of the time showing when the system is idling?
I think that the computer is the one that consumes the most power.
Because I want to be kind of 100% honest with you. I feel like almost every part of the system is up to the definition of professional design. My only slight concern is on the idling current draw. It's like, you see what I mean? You've done wonderful work, don't get me wrong. I'm your advisor, I know that, but that's, if you want me to really be picky and say there's one weakness of the entire system, I would have to, you see what I mean? It's that current draw, it's idling. I'm not 100%. I feel it's pretty safe, but that's like, you have to kind of gently make sure that the user understands that, because which is the idling current.
I think some power consumption calculation that are stated in the appendix. Let me show you. Like for example, right here. This is like the worst case scenario. As you can see here, I'm assuming that the solenoid is like energized for 10 hours, and the valve printing for 10 hours, which is not of course the normal scenario. But I also mentioned that the ideal mode, the current of the printer is like 0.004.
Do you recall like when was idling? What was